Thanks for your patience. So we're going to try to do our best to emulate Amy's success with past years of this session. I hope you enjoy it. We're really excited about the wonderful people who've agreed to speak today, starting with Lindsay Neld from Earthmover, who is a software engineer who works on Array Lake and other open source solutions. So thank you so much, and please take it away.
Okay. So, hi everyone. Today I will be presenting on Zar and IceChunk as foundational cloud native tools for Earth science data. I also want to say thank you for inviting me to speak at my first ever ESIP conference. Already it's been a lot of fun. So I'm going to give a quick overview of where we're headed today. First, I'll talk about why Earth science data, because of its sheer volume, complexity, and collaborative nature, needs cloud native solutions. I'll then introduce Zar and IceChunk as an answer to some of these cloud native. Full screen.
Thanks.
All right, I'll introduce Zar and IceChunk. Okay. And then finally, I'll introduce a case study that we did with NASA that resulted in 100 times faster time series access with IceChunk. But first, an introduction. So my name is Lindsay, and I work as a software engineer at Earthmover. I previously have held roles as a machine learning engineer at companies like Pachama and Maxar, specializing in climate and geospatial data science. And through these roles, I learned that I really enjoy building ops tools and data pipelines to enable scientists and researchers to focus on discovery more than data processing and infrastructure, which is how I ended up at Earthmover. So Earthmover was founded by Ryan Abernathy and Joe Hammond of Pangeo and other open source renown. And the mission statement of the company is to empower people to use scientific data to solve humanity's greatest challenges, which funny enough seems to echo ESIP's mission that they presented this morning. And I really resonate with this empowerment piece. Often the scientific data that we're working with at Earthmover is Earth science data, and our role is to make managing those data systems as seamless as possible. So the Earth science data that we work with at Earthmover can take many different forms. A lot of it is atmospheric in the form of weather, wind, precipitation, satellite observations of clouds. We also work with oceanographic data, like sea surface temperature and currents. In my previous role, I've worked with a lot of ecological Earth science data, such as canopy height and forest cover. And what strikes me about these categories of Earth science data is that they are all multidimensional. They all tend to have a time dimension, a latitude, a longitude, maybe an altitude or depth, and then the actual variable. And at Earthmover, we like to represent that as a data cube, or in this case, a Rubik's Cube. And this is a great model to work with because we can visually see that we could have a latitude, a longitude, and a time in our data. And this makes sense because Earth systems vary over space, time, and depth. And so these variations are naturally represented by arrays with multiple dimensions and not necessarily tabular data that we see in the more business world. Furthermore, I figured since we are participating in the Foundational to Emerging Cloud Native Technology session, I just wanted to cover what it means for data to be cloud native. And one really important thing to understand here is that latency with object storage is much higher in cloud storage than on a local file system. So when you're reading data from the cloud, you have to send a GET request. And that GET request can take a handful of milliseconds from the moment that you send that request over the network to the time that you get your first byte of data back. So at its core, cloud native data is designed to be accessed efficiently over these HTTP protocols and also processed in parallel without needing to download the entire data set. And what it means to be cloud optimized is actually a much more nuanced conversation than what I've presented here. So I linked a fantastic blog post that my colleague Tom Nicholas wrote on the subject, if you want to get into some of the grittier details of it all. But why does this matter for Earth science? The simple answer is that Earth system data volumes are exploding. So NOAA's NCEI archival volume is projected to surge from over 44 petabytes in 2021 to over 1,000 petabytes in 2030, with an annual ingest accelerating past 200 petabytes per year. In a similar vein, NASA's archival data volume also surged from 15 petabytes in 2015 to over 100 petabytes in 2022. So not only is this archival volume of data growing, but more and more of this data is being migrated to cloud object storage for its cost benefits. However, most scientific array data formats like HDF5, NetCDF, GRIB predate the cloud and thus were not designed with cloud object storage access in mind. This means that these archival formats often don't work well with cloud object storage due to the high latency of HTTP calls. So while these traditional formats have long served the research community well, as data grows bigger and we start moving it to the cloud, new tools are needed. And this is where Zarr comes in. So Zarr is an open source cloud native data format for multidimensional array data. And one of my favorite fun facts about Zarr is that it was actually developed for genomics, but now fits a wide variety of data that can be represented by a data cube model, much like Earth science data. So Zarr is often referred to as Parquet for arrays because it stores data in chunks rather than large monolithic files. And we can kind of think of these chunks as smaller, manageable pieces of this larger data cube. So it could take the form of one of these subcubes within the data cube or any slices along any of the dimensions. And because data is chunked, we can then read and write to these chunks independently and in parallel, which then allows for scalable access patterns in cloud object storage. There's no limit to the size of Zarr arrays, and Zarr is also compatible with common tools like Xarray for array analysis and DAS for distributed computing. So Zarr is not necessarily a data format per se, but it's more of a specification or protocol. So at its core, Zarr stores data in chunks, which are in binary files, and these chunks are compressed to save space. And then the entire data set is organized in a hierarchical directory structure with simple metadata JSON files at each level. And because we have metadata at each level within the data set, we're able to traverse and discover and read in data sets without actually having to read in the whole data into memory, which is really, really ideal for working with larger data sets. Furthermore, the structure also scales to cloud environments where each chunk can be a separate object in S3, and then you only have to read and write to the chunks that contain the data that is of interest for your operation. So how does IceChunk fit into all this? To understand the role of IceChunk, we need to describe a scenario which we often call the multiplayer mode, which arises in a team setting. So imagine that you have a user A that starts writing a large update to a Zarr data cube. And this large update will modify many chunks across the data set. And this write takes time and happens incrementally. Meanwhile, before this write is finished, another user comes in to read that data set. The resulting data set that user B gets back is a non-atomic view of the data set. Some of the chunks have been updated and some of them have not, which means that there's no well-defined version of the data that user B is using. And so if user B ends up using this copy of the data for some sort of downstream analysis, this can produce a lot of inconsistencies. And this problem arises because Zarr is not a file format. It is a data set spread over many different files that can be read and written to in parallel. So this is exactly the kind of problem that IceChunk is designed to solve. So IceChunk brings transactional guarantees to multidimensional array data. Updates to an IceChunk data set are atomic in version, so either you see the full update or you don't. And readers will always see a consistent snapshot no matter when they access the data. And I find it helpful to think of IceChunk as kind of like Git for data sets. So when you have a GitHub repository and you're writing code, you have to commit that code to Git for anyone else to come along and extract that code from you, right? And that's the same thing that happens with IceChunk. Before anyone else can read the data updates that you make to a shared data set, they would also have to check out that specific version of the data set that you've committed. So this brings Git-like version control with like branches and tags to the data set. IceChunk is also open source, and its core is implemented in Rust with a very lightweight Python wrapper, which then lends itself to optimal I/O performance within cloud object storage. Like Xar, IceChunk is also compatible with Xarray and Dask, and it also supports virtual file references via integration with virtualized Xar, which I'll talk about in a second. And so I think to really understand IceChunk, it's better to look at the code, which I know might be a little bit small up here. But basically in IceChunk, what you have to do is, all you have to do is define a storage backend. So that could be your local file system or a cloud bucket. Here we're doing an S3 bucket. We then create an IceChunk repository, which is essentially, you can think of as like a Git repository that represents a versioned data store. From that IceChunk repository, you can then open up a writable session. And that means that any of the changes in your session that you make to the data set belong to that session. And those will not be committed to your data set until you call session.commit. And when you do that, a serializable hash is then associated with that commit to your data, which means that someone else can take that commit and check that out themselves and know exactly what version of the data that they have. And because we have this series of commits for incremental updates to your data set, you can then check out different versions of the data and time travel along your data set's history. And so at the beginning of the month, we just released IceChunk 1.0, which means that it is now ready for production grade use. So we're super excited about it. We'd love for you to check out the repo. And then along with this release, we also made available an Era 5 ECMWF forecast dataset. This is an IceChunk dataset, and it's through our Array Lake, our EarthMovers like Array Lake platform, and it's totally free and public to use. So if you want to like get your hands on a very large IceChunk dataset, you can sign up through Array Lake, or you can come talk to me. So this is all great. But a lot of earth science data is historical data stored in archival data formats like NetCDF. And now all these files are being moved to cloud storage from on-prem storage. And because these are not in a cloud optimized format, this leads to a lot of performance penalties. The client code has to look through all the metadata spread throughout each file. And as data gets larger, this just simply does not scale. So take, for example, if you had 50 terabytes of data spread across 500,000 NetCDF files. If it takes 1 minute to read per file, which is what we found in testing, to be able to read the whole data set from cloud storage could take over a year. So you might think, we could just rewrite this into Xar. And you totally could. The time to open the data set would reduce from 1 year to less than a second because of those hierarchical metadata files. However, you effectively double your storage costs because now you're hosting 50 terabytes of NetCDF data and 50 terabytes of Xar data on cloud storage, which kind of negates the purpose of the cost savings in the first place. So what if the data just looked like Xar? This is the idea behind virtualized Xar, which Max is going to give a whole presentation on in a few minutes, so I'm going to run through this very quickly. But virtualized Xar is also open source, and it's been a community-driven effort. And the idea behind it is that we could cloud optimize data while avoiding actually rewriting or copying this data in cloud storage. Virtualized Xar works by reading archival data and extracting virtual chunks, which are basically pointers to the bytes in the archival files. And then these virtual chunks can be loaded into IceChunk directly and then gain all the benefits of ACID transactions and the Rust I/O backend. And how this works is that it just writes a lightweight index that makes the original data look and behave like Xar, but doesn't actually rewrite any of the physical data or turns the data into a physical Xar store. And so to illustrate how powerful IceChunk and virtualized Xar are, I wanted to introduce a proof of concept that we did with NASA a few months back in conjunction with Development Seed. So over the past few years, NASA has been migrating petabytes of archival data from on-prem storage to the cloud, in part for storage cost savings. And as we saw earlier, cloud storage is expected to surpass over 300 petabytes of data in 2030. Unfortunately, a majority of this data is in archival formats such as NetCDF. And so NASA faces this problem where they want to optimize cloud native data access, but they don't want to do a costly and complex data migration for all this historical data that they have. And so the GMP IMERG data is one such example. So this data set is a global estimate of precipitation every half hour. And each snapshot is distributed as a single global NetCDF file. So currently, users access this data by going through NASA's Giovanni service, which extracts the data from, it lives on on-prem storage, so extracts it from there. And so when a user sends in a request over an AOI, they end up getting a month-long time series of precipitation data back. This could be up to 1,488 files for a single request. So if we were to move this data set from on-prem storage to the cloud, we have a few options. We could keep them all as NetCDF files and try to access those NetCDF files directly from cloud storage. That would mean that we'd have to download all 1,488 files, which would take a very long time. We could transform the data to a physical ZAR store. However, like I said, that would be a costly migration and would end up effectively doubling costs. And then NASA also considered elastic block storage, which you can kind of think of as like hard drives for the cloud. And it's more similar to like POSIX storage than it is for cloud storage. So it would make this migration easier. However, EBS is 20 times more expensive than S3. So this would also negate the cost savings of moving to the cloud. So NASA partnered with Earthmover and Development Seed to pilot an approach to address this problem using IceChunk and virtualized ZAR. So we first use virtualized ZAR to scan these data set files and produce an index describing the precise location of all the data within each file. And then we store these data as chunk manifests in IceChunk's optimized format, basically being able to present the entire collection of data of over 1 million files as a single analysis-ready data cube. We then leveraged IceChunk's optimized Rust-based I/O engine to enable thousands of data requests to be issued in parallel in just seconds. And the results here are actually quite stunning. So to extract a 1-month time series from this IMERG data set using this IceChunk approach took 3 seconds. If we were to try to extract the same data from the set of NetCDF files on the cloud, it would take over 5 minutes to get that same set of data. And then the control, which is just those data sets on POSIX storage, took 45 seconds. And so we can see that this cloud, this IceChunk plus cloud approach is still much faster than what NASA has today. And so this proof of concept just shows that there is potentially millions in cost savings for using IceChunk and virtualized ZAR to handle these massive volumes of archival data formats, and also ends up having an end benefit to the user in terms of efficiency. So I want to wrap up by just kind of going over of maybe when you should consider using IceChunk, ZAR, and virtualized ZAR. So we recommend using ZAR as a data protocol. If you're working with large n-dimensional array data, if you need fast and chunked access, if you're working in a cloud environment, or you're using parallel and distributed computing. And then combined with IceChunk, it adds version control and transactions for a distributed team setting, as well as support for virtual chunks. And then finally, virtualized ZAR can cloud optimize data in archival data formats, if that's the kind of data that you're working with. So together, these tools offer a scalable cloud optimize, or a pathway to scalable cloud optimized analysis in earth science and beyond. So thank you. Yeah. I do want to note that this presentation is loosely based off of a blog I wrote that is called What is ZAR, that goes into the details of what the ZAR data protocol is, why you use it, when you'd want to use it. So I also recommend checking that out. Okay, thank you.
Thank you, Lindsay. That was awesome. I think we have time for one question, and then I believe you'll be around for the whole conference. So I encourage people to chat with Lindsay throughout the week. Does anyone have a question either from online or from the audience here in person? Yeah, Eli.
Yeah, so for the virtualized R, are you stuck with the chunking and the archival data? So like this one big file, are you kind of stuck with that?
So my understanding is that Virtualizar does use the underlying chunks that are used within the file itself. I don't know, does version 2 change that in any way?
Currently, there's still the same limitation, but the some researchers at the French Space Agency, CNES, just put out or are working on a library that splits netcdf files into subchunks. And so then you can store a seed for the decompression algorithm, and you can actually create smaller chunks than the native files, which I think will be like really kind of impactful. Thank you so much.
Yeah, thank you.
for the round of applause. I also want to thank Lindsay for being so gracious in my interruptions in the beginning. Thanks for handling that well. I'm going to try to switch over the screen sharing. And we have as our next speaker, Joe Kennedy, who's a researcher and software engineer at the University of Alaska Fairbanks. And I'm so excited you're here. Thank you.
You can share the whole browser and open a couple links.
Okay. To be honest, you might be better at this than me, but it's been a minute since I've used, this is the application. Okay. I'll try not to interrupt you. Thank you.
It's okay if you do. Hi, I'm Joe Kennedy. I am at the Alaska Satellite Facility, which in addition to being a NASA DAC for synthetic aperture radar data, we work a lot with the research and science applications community and help facilitate them working with our data, NASA data in general. So I'm going to talk about the It's Live project to start, which is a large project that, how do I advance slides? That is led by Alex Gardner at JPL. There's about a dozen of us on the project. I'm going to only talk about half of it, which is the ice sheet velocity part. So there's about 5-6 of us on that part of the project. So the idea with this project is to provide automated low latency global glacier velocities. Low latency being kind of an ill-defined term, which I'll get into a little bit more. But basically we have this constellation of satellites from a variety of different agencies that all look at glaciers in some form, and we can derive velocity estimates from changes in the surface. So it's a pixel offset tracking algorithm. You got an image, you get another image, you see how much a pixel has shifted in those two images. Pretty straightforward kind of science application here. I want to show off our data portal, and I'm going to really talk about sort of how we enable user data access. That's kind of what this talk's going to be about, and it's going to really build on top of what Lindsay was just discussing, which I can't thank her enough for such a great intro to kind of the things we're going to talk about. So we have this data portal. This is in the browser. You just saw data load live. That data actually just went out, hit a ZAR data cube, and loaded the data live as you saw that. So I can actually clear all the markers. That'll clear the data. I can come and draw a couple points, and then just immediately the data comes. So I'm getting a full time series back to 1985 of the velocities over this glacier for this point. If I zoom out, I can scroll anywhere in the world that there's ice over a couple kilometers in size, click on a button, and you'll get this time series back. I hope online saw that. So kind of what are we doing here? How are we getting this time series back? So we got a satellite, it takes an image. Flies by a few more times, takes a bunch more images. So over time, we're building this stack on the Earth of these images over this spot that we looked at our point. Now, hopefully, the data providers have discretized the stacks into a nice geostationary reference so that I always can look at the same spot on Earth and I know where all those images under there. That doesn't always happen, but most of the time it happens. So Sentinel-2, we're talking about tiles. Landsat, this is a specific path and row. When NISAR comes online, this will be a particular track and frame, right? It's just a tile, it's a data cube. We're talking about velocity data, right? It's not just direct satellite data. This is a derived product. So I'm going to do a small aside on how we get to the derived products, which is data provider produces some data. They put it in a cloud bucket right now. We're talking USGS right now. And then USGS nicely gives us a little broadcast message that says, hey, I threw a new granule in the cloud for you. And so from that message, I can automatically trigger in an event-driven kind of standard workflow, take that message, maybe apply some initial filtering. I throw that message into a queue. That fires off a Lambda, just a Python script. It's like maybe 200 lines of Python code that looks at that message, says, cool, I've got a new image. Let me go find some information about that image. I'm going to also go back and search the stack catalog and find all of the subsequent images from previous acquisitions in that same spot back to a year and a half. So I have every 8-day repeat cycle with Landsat. So I've got 64 potential pairs of images I can process. Get those pairs of images, run them through our like cloud-based processing pipeline that does the feature offset tracking, pops out maybe 64 velocity estimates, right? And I'm just accessing the data in the cloud. We're processing in the cloud next to it. This is all super fast, and it shows up in an AWS Open Data Bucket that is sponsored by AWS. I can't thank you enough. This is essential to this project. And now it's easy, and everybody can just access it. So that low latency we're talking about, our ability to go from a new satellite acquisition from the time USGS publishes it to making data available to users in this space is 15 minutes. Using this workflow for all 64 of those pairs, right? So when we're talking low latency for Landsat, we're talking minutes from the time the provider publishes it. So I just told you that I'm making 64 new granules for a talk that I titled Beyond Granules. We've actually made 36 million more granules as part of this project from all the missions. We're doing Landsat, Sentinel-2 and Sentinel-1 right now. We're making 20,000 new granules a day with this event-driven pipeline. So I'm going to talk about how we're getting away from the granules, or would love to get away from the granules. So we're back to this. We want to extract a time series. We have our web app. We click our point. What we're doing is figuring out where on the Earth that point is. And then once we know that point, we've got a nice stack of data underneath it. We can extract through that stack of data, just that time series point, that pixel from each image. And what pops out is that time series thing. So how we're doing this, the essential technology, which is what this session's about. So we've got a ZAR data cube, which Lindsay just gave us a great introduction for. It's chunked along the time axis. So I can actually just hit that one specific pixel and pull the entire time series out of that ZAR data cube as one request. And then with, well, 2 requests, you got to get the metadata up front, and then you get the chunk after that. And then we return that straight back into the web app. So this is actually really easy. There's not a lot of money involved in this because this web app is hosted. It's just a static website. Throw it in an S3 bucket, throw it on Google or on GitHub pages, whatever, it doesn't matter. It's just doing a really simple JavaScript, grab the GeoJSON that tells you where it is, intersect that point, open the ZAR data cube, return the thing. So this all works super fast. So I want to talk about something similar that's happening kind of in ASF, the NASA DAC. This is the displacement portal. So Opera is a project led by JPL to process Sentinel-1 data, radar data. And one of the data sets they're producing is displacement. So surface displacement of the Earth. And I've got our nice data search portal here. I can zoom in on Hawaii. Let's go fire instead of ice this time. And I have this nice stuff happening on the mountain. I want to click a button. We're going to wait a few more seconds this time. And we'll get a nice displacement time series. Just a few more seconds. Maybe. There we go. That was still pretty quick, noticeably a little bit slower. The thing that's happening here that's a little bit different is now, and I do need to do a shout out. I am not involved in the displacement portal. This is a large collaborative effort across the whole vertical slice of ASF. Kim Fairbanks is online attending this session virtually. She's been integral to this project. If you have questions about it specifically, ask her. And she would love to chat with you. So this same sort of thing, we got a web app in the front. This time we're backed by a thin API. Reasons for that are largely for future plans, which I'll talk about in a little bit, but also we have auth in the loop here with NASA Earth data. And by deploying an API, we can hide behind that auth portal and access data a little bit more efficiently. We're still using a little in-memory GeoJSON so that we know where to go on the Earth with a simple in-web app, in API kind of intersection of the point. And what now we're doing is we've got a Kerchunk reference stack, a virtual stack. Virtual Czar is the new version of this, that goes and extracts all the data from all these netcdf files. Opera team has been very good about the way they've designed these netcdf4s. They're cloud optimized HDF5 under the hood. They made sure that that was all done. But because we have to go to all these different files and extract that particular chunk that we want, we have a little bit more latency involved in the loop. But we're now accessing every Sentinel image all the way back to the start of the mission in 2014 and getting a nice time series of displacement, this other derived product. And we really want to be able to do this kind of everywhere, right? Like I should be able to go to a NASA data set in a Jupyter notebook, say, open this data set or find me this data set that covers this area in the Earth, and then just open it and I can do my science. I want my time to science to be basically zero. I don't want to have to fight data to get there and portals and auth and all this kind of stuff. So there's a bunch of patterns of this kind of stuff happening in a lot of different communities, different places in NASA. NSIDC, I want to give a shout out to. They've done a lot of work with cloud optimizing. They've just re-released ATL03 for MySat2 version 7, which is now cloud optimized HDF5s. So you could do a lot of this similar pattern. Earth Access is trying to build in Virtualizar support directly, maybe IceChunk, and using DMR++ files that already exist in the archive to do this data chunking thing. So we're seeing a lot of communities, and in the ISAT2 world, IcePyX is also involved. The CryoCloud has been doing this a bunch as well. But that all kind of works for a time series, right? We've chunked our data, we got a nice time series, but what if someone comes in and draws a circle and they want to know the average over that circle? Well, now they're loading the whole freaking cube, right? Because our data is chunked along the time series. You got to pull the whole chunk. Now I got to pull every single one of those purple stacks to look across that whole cube. So that is super not great. And this is the two data set problems, right? Like when you cloud optimize something, what you're doing is you're optimizing for an access pattern. You're not actually optimizing the data. And so if you optimize for an access pattern that's time series, that works really great until you try to do a spatial time slice. Whereas if you optimize for a time slice, that works really great unless you try to do a time series. And so you can turn this knob back and forth and it's counter to each other. So a lot of people just put it in the middle and kind of have meh access in general, but then it works. You don't have really bad in one way. So if you know your access patterns, if you know your user community and your data really well, you can make the data sing. If you don't, you're going to have problems. This same problem, when we look at our discretization of the world, shows up in cataloging. And I don't think this part of the problem gets talked about enough, which is I can make a collection for the whole world. I might have 36 million granules in that, and then searching through that 36 million granules to find the stack of them that I want is now really poor. Or I can make 2,000 different collections for different cubes of the Earth, and getting that cube is really fast, but now I have to do cross collection searches, which is really slow. So this knob also applies to how we even search and discover the data. And so if you're a data provider, all you've got is problems, effectively. Deploying these portals costs money. You've got engineering effort into them and time. we're getting to the place with discovery is hard with the cataloging and the data chunking. Appending the data, as Lindsley talked about, is really hard. I've got a czar in the ItsLive project. Every time we want to update that czar is a significant amount of effort. So we're doing that like monthly-ish right now. Whereas we'd really like to just stuff a new granule in that cube every time it shows up. So I think we might be doing this. And then you've got your chunks. You have to think about your chunks, right? Like you can't get away from the underlying chunks. And you need them aligned if your images shift around, if you get any jitter or that kind of stuff. So my chunk in one image is not the same chunk in the next image. If I'm doing the virtual thing, then all of a sudden you're opening a lot more data as well. And so we've got some solutions now that are making this in the technology space a lot easier. IceChunk has solved the appending thing. So we're really excited to adopt it. We just haven't gotten there because there's no R or Julia readers and we have large user communities there. The web app thing, we can just do it all in the browser. It all happens in the users. There's no money associated with it really. But discovery and aligning chunks, I think, are still the major challenges, and how we do that is kind of what I'm interested in trying to tackle. So my overall takeaway, I didn't really talk about this all that much in the overall picture, but I do have an AGU talk I gave to talk about the social aspect of this. But you can take a small team of a few engineers, build a near real-time processing application like we did on ItsLive, and we can facilitate this continuous stream of data. We don't have to think about granules anymore. You can just get your time series or your time slices that you want. But all of this has a big if. And all that if, which I kind of hinted at with all of these technology problems, is actually a social problem. That the engineering goals, the technology solutions and things that are associated with it all have to align, not only with the data provider, like how they've made the data, the services they offer it on top of it, how they maintain the data. The cloud business model, we're all stuffing things into the cloud. Egress, for example, is how they make a lot of money, right? So now we want to be able to get people to the cloud to process next to it, so we don't have to pay a bunch of money. Institutional policies, sometimes we can't just compute in the cloud because our institution doesn't let us do it. Or maybe we have security problems, means we can't process Sentinel-2 in Europe. So now we have to pay egress to get it to North America, and that doubles the product cost. Or you could give the money to us. We don't have those. Oh, nope. Money transferring costs overhead. So now we're stuck. We've got all of these money transfer problems that really are already solved in the cloud. We can just do it. We can deploy to Europe. It's not hard. It's a button, but we can't use it. And then all of this doesn't matter. All of this work that we do on the technology, data provider side, processing missions, blah, 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 if our community doesn't adopt it. So the technologies also have to be injected into the community, and they have to be well supported and liked by the community for this all to work. And that's my overall takeaway. I will add this: if you're battling these problems, we've got a lot of experience, so I'm happy to help you, and maybe you'll help me along the way too. And that is it for me.
Thank you, Joe. I think we have time for 1 to 2 questions, and I'd like to invite the people online to have the first chance at asking a question. So if anyone wants to either type in the chat or just preferably unmute yourself because it'll be faster, please go ahead and do so. I'll give you, yeah. Let's see. Also, no, it's a little more pressure to unmute yourself on the Zoom call, so we'll see. Does anyone in person have a question?
Stunned everyone into silence.
That was too good. We need some time to think about it and digest. Thank you, Joe. Oh, Julie. Yes, you can. Let me find you a microphone. Oh, Brianna's gonna bring you in.
Thank you, I've never heard about we talked about, you said cloud optimized means optimized to an access pattern and space defined. Are there other access patterns or is this too?
Okay. I think like Lindsay pointed to, there's a lot of higher dimensional data sets, right? Like I talked about very specifically, like we got our two space axes and our time axes. So we've optimized a long time or along that spatial day. But if you now start adding in a bunch of different variables on top of that, then all of a sudden you have a lot more complicated things. So like ice sheet modeling or system modeling world, like now you have altitude bands, precipitation, ocean levels. Like it's really hard to take those high level data sets and optimize for a usage pattern. Usage gets so high. I'm sure this is all.
Just out of curiosity, where would you rank your problems with Earth data login in your list of issues?
I should maybe not answer that question. No, so the reality is Earth data login solves for NASA some particular issues that have to do with access control. We do have restricted data. We also want to provide metrics to our sponsors, which is Congress, right? Who's using the data, how, and that kind of stuff. And it's really hard if you throw auth away to do a lot of these kind of things. Auth for czar becomes really problematic, right? Like every object is its own unique URL because it's its own object, right? And that means there's an auth loop, a new auth loop for every chunk of data you access. So Earth data login and virtual czar, or even just czar in general, has a tension, and like getting around that's harder. So a way that like USGS has solved this issue is to have requester pays buckets, but then then now people have to pay for data unless they're processing, because then you can just get straight to the data. So NASA's exploring that kind of stuff, but there's more, I think, built into Earth data login and the benefits and drawbacks of that than just like it's slowing down my data access, though that's what I hit most of the time. It really doesn't. No, it's not number one for sure, but it's up there.
We also have a 4 p.m. session where we won't record every single statement. So if you want to talk more about that, then. Okay, I guess, yeah, I'm next. I'm gonna talk a little bit about the major release of Virtualize-R that we put out yesterday. For those of you who I don't know, I'm really glad you're here. My name is Max Jones. I'm a cloud engineer at Development Seed. I'm also involved in various communities like Cloud Native Geospatial and Pangeo, and I develop open source software, including Virtualize-R and Czar. And so that's why maybe Joe looked at me when he was complaining about Czar. Sorry, Joe. So yeah, just a quick overview. I'm gonna try to not duplicate material with the other talks. So some of this will go pretty fast, but I'm gonna talk about why virtual czar is a concept. This you may have gotten a gist of already. And then why Virtualize-R as a library exists and why we did a major release yesterday. And then quickly show another example of virtual czar in action and talk about what's next. So you've seen this, right? Like users want the quickest way to the insights as possible. And that mostly involves operating and thinking about things on the terms of data cubes and time series. But models and Earth observations come to us as individual files or streams of data that are easy to aggregate into individual files. And this it doesn't scale well on the cloud. And that's what a lot of the presentations so far have been talking about, is that in order to get people to quickly get those insights and analyses done, we have to put a lot of money and we have to put a lot of engineering time into APIs and services to provide that adaptation between original files, low-level data sets, and easy-to-use services. And we have been putting a lot of time and effort into Czar, both native and virtual, because we think it can help in solving this problem. by providing harmonized and cloud optimized data access on top of archives. And Virtualize-R is a utility that allows this to happen. So it produces the data model that is harmonized across different data formats, so that a user or doing science or using X-ray or a UI on the web or a stat catalog only has to know how to interact with one data model versus every data model for every file format in existence. And there's various steps that go into that process of producing that harmonization layer. And I'm going to go into them in a little bit of detail because it's really important for why we put out a major release. So the first step in creating a virtual czar is to build a czar representation. So a virtual representation of the native file format. So this is netcdf, TIFF, GRIB, etc. And this is the very hard part. This involves reading hundreds of pages of specifications and mapping it to czar specification. And it's really important to get right. And it should be a distributed community effort. So, and it should be support open source implementations. It should also be pluggable so that someone could build this mapping for their own proprietary data format and save the same money as everyone else who can work in the open. The second step is combining the virtual representations of individual files into a single data cube. And then oftentimes you want to persist this virtual data cube to disk so that you can either use it again yourself later or you can share it with other people. And then lastly, you need to understand how to interact with that virtual data cube so that it can be used by UIs, libraries, services, etc. So here we have those different steps laid out from left to right. You have file parsing, concatenation, serialization, and loading. And many of you know that Kerchunk was a predecessor. In some ways, it still exists, and there's still a lot of work going into it to Virtualize-R. And I wanted to just answer this question, like, why Virtualize-R? Like, Kerchunk exists. And the reason Virtualize-R was created was to simplify this concatenation step specifically. So the process of going from multiple files to one files is the same as going from a single array to a data cube. And that's a problem that X-Ray solved 10 years ago. And we wanted to, or Tom Nicholas in particular, was inspired to bring that benefit and simplicity of X-Ray to the virtual czar ecosystem. And Virtualize-R was created only to solve this problem. Like, frankly, problem with Kerchunk and Virtualize-R was that it solved all of these problems at once, and that made it really hard to maintain and extend. So anytime someone wanted to create a new parser, they would have to create a pull request to Kerchunk or Virtualize-R and ask the maintainers to review their interpretation of GRIB. And we'd be like, I really prefer netcdfs. Like, I don't. So we want this to be fully extensible so that each individual can write their own parser, their own serialization, or their own loading utility. And that is why we put a lot of time into Virtualize-R 2.0. Also, I do really appreciate GRIB. Her is a great data set, and I didn't mean that seriously. No preferences between file formats. So Virtualize-R 2.0 maximizes flexibility and extensibility, and I'll just go into a couple examples of what this means. So some of you may have seen Ferris the Crab. It's Rust. The language is unofficial mascot. And the way Pete Godomsky has explained it to me is that Rust can really help us by being used in very key parts of a workflow. So we shouldn't try to rewrite everything in Rust, but we should identify key performance gaps and use it there. And so an example of this is Kyle Barron wrote async TIFF reader that can speed is like the fastest access to TIFFs currently. And so we can now, with Virtualize-R, use that just for this parsing step, completely independent from Virtualize-R. We define a protocol so that you can implement your own parser. And so I did that, and you can use all these performance benefits. Like you can see the higher bar is the throughput of async TIFF, and the lower bar is the throughput of raster IO. So that type of extensibility allows these like really key performance impacts and targeted performance impacts in particular. Another example, you can plug in your own components for loading. So for example, as part of this, we wrote like a functionality to go directly from the Czar data cube that Virtualizar produces to a loadable data set. So you don't have to temporarily serialize it to Kerchunk or IceChunk, again, using Rust. And just like for the Y, this is some simple benchmarking I did showing OBSTOR versus FSSpec, showing like over 3 times as fast data loading when you can use Rust in this very targeted and specific way. The other reason we wanted to move to Virtualizar 2.0 is because it's fully integrated with OBSTOR, and we really like how OBSTOR is rigorously typed. So for example, here you have auto-suggested AWS regions and auto-completed AWS parameters, and we think that this will improve the reliability of code, but also speed up developer experience. And lastly, the last component of extensibility is on parallelization. So if anyone here has ever used OpenMF dataset, you can specify an executor. And so here you can parallelize the parsing of individual files over using Dask, lithops, or your own custom executors. And so this is extremely parallelizable process, and because of that, it can minimize costs and maximize benefits. So this is another component of the case study that Lindsay mentioned, where Amy Barchauskas produced a virtual Czar for the 22 years of the extremely high resolution 0.01 degree MirrorSST data set, and that cost $1.23 to make, and it costs $4 a year to host, and it speeds up access by over like 100 times, which reduces the amount of time you have to spend on computation during services, speeds up developer time. And like that's, I'm like so embarrassed that that's less than the amount I spent on an oatmeal latte this morning. Like that is pretty cool and also sad for my personal decisions. But so that is like the component to tying it into services. And we also think that this has impact for a scientist workflow. So we've been working with a Beta project to adapt these stories. So for example, Julius Busecki showed that when you use Virtualizar in this science workflow for the analyses of derechos, you get a 40 times speed up on opening the data set and then a 3 times speed up for computations. And I think the important thing to remember here is that scientists run their workflows many times as they're iterating over them. And so you get this speed up every single time and just don't have to wait as long and not have your train of thought interrupted as you're waiting for data to load. So we put a lot of technical effort into this, and I was gonna like have this slide be, now I get to do the fun stuff, which is helping people adopt this. But then people were like, oh, we need variable like subtrunking. So there's also key technical things we're gonna work on, and I will mention them real fast. One is the subtrunking component, and the other is variable length chunks. Like for example, the chunk for MirrorSST switch during time. And we think that it's very practical and beneficial to develop a Czar extension that will support that type of virtualization. But really, I think it's time to prove this out, and it's time to get this so that it's not in like a few people's hands. It's like anyone can run it and anyone can use it. And that happens through like people who are connected with each other already and supporting each other. So I would be really thrilled to work with anyone on this technology. And then, yeah, the part 2 of this session is going to be whatever people want it to be. One option, I prepared some examples on Virtualizar 2.0 that I'd be happy to walk people through. And then, yeah, as I mentioned, I work at Development Seed. I think we have a job posting open for a front-end engineer, so I promised I would put these slides in. It's a fun place to work, and I hope we also have a general application that's always open, so it'd be cool if people think about applying. Yeah, maybe one question, and then, yeah, go ahead.
Let me know.
So in terms of getting it into lots of people's hands, any thoughts about how to integrate it with sort of other foundational geospatial software like GDAL, which would automatically get it into all those layered applications?
Yeah, I submitted a proposal last Friday for a czar summit that I'm hoping will get funded. And we already confirmed Evan Roltz, who's the primary developer of GDALS. And if you know anyone who's also contributing to the funding for that event, like let me know. But yeah, so really collaborating with Evan, I think, is the way to make it as broadly usable as possible. Okay, well, thanks for listening. Can let me try to mute us and then, okay. I'm really excited that next we have joining us Tasha Snow, who's a research scientist at the University of Maryland and NASA Goddard, and is a founder of CryoCloud. I'm hugely thankful for all the work she's put into this and that she's agreed to present today. Tasha, hopefully we can hear you. Do you mind going ahead?
Yeah, can you hear me? Cool. And you can see my presentation, the correct version of it? Yeah, awesome. All right, thanks, Max. And thanks for inviting me. This is such a cool session to be a part of. And I love everyone's work. I'm always like astounded by everyone's work. I'm Tasha. Max already introduced me. I'm the co-lead for CryoCloud. I'll be talking to you today about how we can leverage a communal cloud-based Jupyter Hub to build a thriving scientific community. And that's kind of drawing from the work that we've done with CryoCloud, as well as collaborations we've had with other Jupyter Hub leads, including Eli, who's next after me. I want to start by first acknowledging all of our collaborators on this, as well as our funders. So jumping in, science kind of looks like this. You have, different systems here. I work in Antarctica. I'm a glaciologist for the other half of my work. There's ice here in the system, there's ocean, there's atmosphere. And these are all really interacting with each other a lot. It's a really interconnected system. And a lot of the questions that are most exciting and also least well understood are at the intersection of these different systems. And so in order to get at some of these important questions, we really need to have interconnected researchers who are able to bridge the gap between the different fields and things to be able to get at those questions most effectively. And so one of the ways that we're proposing to do that, and we've been testing, is to use a communal Jupyter Hub. And this is a Jupyter Hub. And so the questions that I'm kind of answering in this work is, how can a Jupyter Hub with its access to the cloud, what can it do for us? So I'll talk first about advancements enabled by a Jupyter Hub, trends in usage and user experiences that we've seen from CryoCloud, ongoing barriers for users, and kind of wrapping it up, putting it all together into roadmap for a thriving scientific community. So starting out with advancements, the Jupyter ecosystem is really exciting because it's flexible, modular, and fully interoperable with the tooling that it has. So that enables collaboration and also user curation. So it's agnostic to wherever your user might be using it, the data they're using, the programming language, and the tooling. And that's really exciting because that allows for seamless support of a range of communities. So you can have different kinds of users, deployment structures, guardrails, storage, and compute allowances in different Jupyter Hubs to support different kinds of communities. So that's at kind of the community level, but it can also help users individually. So this is kind of a case study with a Landsat sea surface temperature algorithm pipeline that I built during my graduate studies, not in the cloud. So you can see the different kinds of tools, all different kinds of tools that don't really work together, different tasks that I used for that, and the data storage. And you'll notice there's a lot of data storage because it's really slow to create some of these intermediate steps. And so we want to store all of that. And that ends up taking about 6 terabytes of data. And it's a weeks long to months long pipeline to be able to do that because you're manually downloading the data. Now, fast forward 6 years and I've cloud optimized that pipeline. And so now it's orders of magnitude less processing time and data storage. But what's really required to be able to do that is you have the correct code with the geospatial tools that everyone has been kind of talking about. I promise mine is not fully efficient, or fully optimized to the point of what everyone else is doing here, but there's definitely room for improvement. But you also need a platform for working in the cloud optimized data format, which is really an underrated piece of all of this and the most important in my opinion, and data access tooling. And without any piece of this, we really slow down the pipeline. But with all of it together, we can reduce time for iteration, time to solution, and increase impact. With the Jupyter Hub, we can also enhance science access. So one of the cool things we've heard from some of our users is they can get an undergrad up and running on an entire NASA data store in an afternoon. And that is only made possible by having the cloud-ready data and geospatial tooling, the persistent platform and open community, and also the training designed for new users, as well as the accessible state-of-the-art scientific workflows that brings our beginners up to state-of-the-art instantly instead of them having to reinvent the wheel to get there. So that's kind of the advancements we have. And then we run a user survey through CryoCloud and monitored costs and usage to better understand trends in usage and user experiences on the cloud. So the first thing we found, I'll present here, is to show you this. These are the daily costs in gray here throughout the lifetime of CryoCloud. That's on the left y-axis, and we also have the number of daily users on the right in red. And looking through all of this, we found that it costs less than $1 per day per user to actively use the cloud. And it's about $187 annually, and that equates to about users using about 26 hours of compute per month. And if we calculate that out, the operating cost is far less than the price of a laptop that you would have for the lifetime of the laptop. So it actually makes sense to buy a cheaper tablet and work in the cloud than to buy an equivalently resourced laptop that also is not as flexible. Another thing you can learn from all of this is about practices and the importance of guardrails. So I'm showing here, we had workshops and hack weeks and things like that. But what I want to point you to specifically are the yellow lines here. The first one, you'll notice that gray spikes right before the line that I have marked here as instance culling bug. We had a hack week. There was a bug that prevented these instances from culling, and they remained open for a really long time. And we ended up incurring a lot of costs because of that. But once we found that, our costs dropped back down. This is really interesting. Like, we have, the leading cloud experts in the world working on this 2I2C. So this slipped by them, but a lot of IT experts at universities who are not familiar with cloud are actually making decisions to do this all the time for their cloud platforms. And so that was one of the reasons we had CryoCloud, is because a lot of the people in the science teams we were working with actually had universities that were spending a lot of money for them very quickly without them realizing it. Another thing to notice is that when the gray diverges from the red, this is where we have increases in data storage that aren't related to compute. So the gray is a combination of data storage and compute. And you'll notice here in about April that our costs start to spike. And we noticed that some of our users were having high data storage. Someone was storing 4 terabytes of data without us realizing it. And once we caught that manually, obviously our costs dropped down a lot. But that was manual. So what's really important as Jupyter Hubs move forward is to have this cloud cost monitoring systems and also the guardrails in place to prevent people from being able to use this without you knowing it. Because that's a really key piece of keeping science really cheap in the cloud. So on top of that, I said we had user surveys, and I'm only going to give you a few nuggets of what we got from that. I have slides at the back of this slide deck that you can look at if you want to see more of our findings. One of the key findings was that long-term usage increases user literature or literacy with cloud computing workflows and tooling. So in the orange, we have in the green, we have new users who have been in the cloud, working in the cloud for less than 6 months. And they said that their main challenges, which is over here on the left, the main challenges that they had were lack of cloud expertise and skills in using the system. So that's their main barriers. The green are the orange, I'm getting them mixed up. The orange are people who have been working in the cloud for more than 6 months. And their barriers to usage actually transition to more sophisticated things like controlling cloud costs and data not being streamable from the cloud. So we saw this transition over time. And what's really interesting is the last piece of this, the data not being streamable. That's really important because we found that the main motivation for users transitioning to the cloud was so that they don't have to download data or to store data. So we are still having huge barriers to our users, preventing them from being able to achieve their main motivations for working in the cloud. And that's for people across user experience levels. Another exciting piece of information we got from this that was a little bit unexpected is that people were really neutral on having all of their work in the cloud. Some people really wanted to, but a lot of people didn't want to at all. And this speaks to the diversity of people's tool chains and how they're kind of using the cloud as a piece of their workflows, not necessarily all of it. And this is actually supported by trends in data access at NASA Data Center. NSIDC has been seeing increase in their cloud data access pattern or data accesses. And when you break that out into different data products, so in this case, these are ISAT2 data products. The different data products are by color, and the dark is on-prem access and the light is cloud access. And so what you can notice across the top here in this first figure, they're pretty similar between cloud and on-prem. It's even more so in the cloud on ATL4 on the right-hand side there. But when you start to look at user access distribution patterns, or the number of users that are accessing it, there's far more users who are getting into the on-prem data than in the cloud. And so what this tells us is that the cloud is more often being used for big data projects, and laptops are often still the default for small data projects. And this is anecdotally what we've heard from our users too. I don't really understand it. I do everything in the cloud. But yeah, this is what most people are using. Some more insights we've gained are from our Jupyter Hub administrators that we're collaborating with. And I'm only drawing a piece of the information we put together. We've been meeting monthly to build a document, a white paper to talk about, what the main barriers are, ways that we use the infrastructure and future for Jupyter Hub. So there's going to be more in that. And there's some at the bottom of this presentation you can learn more from, but I'll give the key parts that I'm find most interesting in the ongoing challenges for users. So I'm only listing here things that I personally have interpreted as being the common major challenges with no replicable solutions. I prioritize these. So some that came out of that document were around accessing data. So users are having issues because they have download-based workflows still. They have limited support and unavailability of secure programmatic authentication. So you can't actually authenticate to access the data. You still have to download it. Legacy data formats that prevent streaming, and a lack of best practices for accessing large or restricted data sets. They're also struggling with unpredictable or untenable costs when scaling up and managing cloud spending and monitoring it. And these are all things that we could really use a lot of help on. Users are also having difficulty accessing Jupyter Hubs and cloud storage due to limited permissions, bureaucratic hoops, and restrictive policies and uncertainty around how to get needed access. So users can spend weeks to months just trying to get access to data. There's also insufficient IT expertise, as I mentioned before, and institutional support. And last but not least, there's few beginner accessible on-ramps, so it's pretty hard for users to get started in the cloud to be most cost effective. So how do we overcome these barriers? I'm going to give a quick roadmap to kind of the work that we've done in CryoCloud and ways that we've overcome some of these barriers. And a lot of that has stemmed around the idea that social innovation is about 3 times more important in the success of our innovation than technology is. And there's a lot of research that goes into that we didn't do. But what I mean by social innovation is policies, how we get our community to build together, that sort of thing. So in this case, we use Slack for all of our community's communication. And not only do our scientific users use it, but we have our tool developers as well as our cloud engineers in that space. And this synchronous work is really important for doing what we ended up having, or successfully having what happened with Sean Foley occur. He reported on our Slack that GPUs were underperforming. And UV, who's a 2I2C cloud engineer, responded back and forth to him over the course of the next 4 hours. And over that time, he figured out the bug fix. And not only did that, but propagated that to all of their 100 hubs at 2I2C. And then, as you'll see at the bottom, he created an issue at Jupyter Hub and sent it out to the entire open source community. And this is something that happened over the course of 4 hours, right? So by integrating our IT essentially with our scientists, we actually can start to get different users in one space, accelerating the feedback and collaboration. And this creates a shared community resource model where our users don't have to learn about how to build the cloud. They're going to do it far less efficiently anyways. So we're sharing an infrastructure in our costs and in our expertise. And that really maximizes the impact of each research dollar doing this as a community. So we really build an open source community without boundaries and empower our communities to do what they do best. And people end up building together in one direction so that you don't really you get past this closed science model where everyone's creating their own Jupyter Hub, everyone's reinventing the wheel, and you get at this co-creation model where everyone's building in one direction much more rapidly towards a scientific solution. So kind of very briefly, wrapping this all up and putting this into a more of a mental model. How do we break down these barriers and kind of get at co-creation? First, we have built a strong foundation for collaboration by designing a strong technological vision and revising that with the community. Having a welcoming code of conduct, shared and efficient communication space that rapidly gets people to the information they want really quickly and efficiently. And then having the shared environment and computing space. Also investing in the community by inviting beginners and experts from all parts of the tool chain, including the IT, all in one community. Having training that resonates with beginners so that they get to the state of the art really quickly, and having documentation for beginners to contribute and develop. So it's not just the team leaders that are actually maintaining images and things. And then encouraging co-creation by sharing products early and often, making upstream open source contributions, encouraging intellectual generosity, and having a commitment to open source and open collaboration. And all of these are kind of feeding back on each other and reinforcing them. So we're really getting at this idea that social innovation is most important for making scientific solutions happen. But we can really enable this by having a Jupyter Hub shared infrastructure. So as we have these interconnected systems, we think that Jupyter Hubs can really enable having interconnected researchers. So with that, thank you so much.
Thank you, Tasha, for your awesome work and presentation. I think we have time for probably a single question. Does anyone have one?
No one does. I'll have one. I don't know if Tasha can hear this well enough, but
Yep.
I'm wondering when it comes to, you put one of the difficulties of getting institutional support. So how are you actually bringing this to other universities? I'm sure that there are some universities that are specialized in glaciology that you can connect with, but what does that process look like right now?
So I didn't explain this because I didn't have time, but CryoCloud supports 750 researchers and they're geoscience researchers. It's not just cryo. We're going to rebrand soon. And we are onboarding people through hack weeks and through community workshops and things when people approach us to do cloud work and different science teams. So there's not really a specific way we're onboarding people. Some people are also just onboarding on their own because we have recordings for trainings. And funding for that right now has come through NASA, and we're diversifying we're going to have some funding hopefully through Jupyter or some private funding perhaps, or we have some NSF things in place, and then people can bring their own cloud credits too. So we have a bit of a social system where our community also contributes to cloud credits.
Awesome. Thank you, Tasha. Yeah, I'm really honored we have as our last speaker Eli Holmes, who leads open science at the NOAA National Marine Fisheries Center. Thank you, Eli, for being here. Let me try to get your talk up.
see.
Thank you.
Hopefully,
Is
is
this
this
okay?
the right version here? Let's see here. Yep. How do I- does it want to? Yeah, excellent. Okay.
Great, thank you.
Great, great. All right. Hi, everyone. Well, it's really perfect that I am going last because I am going to be kind of weaving together all the things you've heard about and talking about how at an organizational level at NOAA Fisheries, we are trying to upskill our scientific workforce in the kinds of tools that we've been learning about here, because we all know data's going to the cloud. We need to be changing the way that our workforce is interacting with these data, and also teach them the types of cloud computing tools that Tasha was talking about.
We're not screeching. Sorry.
Perfect. Hopefully they're hearing me. All right, perfect. Yeah, that's good. That's good. Yeah,
Thank you.
excellent. All right, those of you online, you didn't miss anything. That was just the title. So a little bit about me before I start, just to kind of understand the perspective that I'm coming from. So I've been with NOAA over 25 years, a statistician with them, mainly developing algorithms, a lot of matrix calculus. As part of that work, I also developed a lot of R packages, very much involved in like creating new algorithms and then creating the tools and the documentation so people could use those. So I've been involved in the open source community for a long time. I've also been involved as an instructor for many years. I'm an affiliate faculty at University of Washington, taught multivariate time series analysis many, many years. And, you know, around in the COVID time, I was trying to figure out new things to do. And I did an online hack week that was organized by OpenScapes. I'd been involved with OpenScapes before, but I did this hack week with them. It was online. And I was like, whoa, wow, like that. That's what I want to do. And I decided to make kind of a pivot. And since 2021, I've really been involved with these efforts at scientific workforce development. And we are now in we just finished year 1 of a 3-year effort within NOAA Fisheries to do this big jump forward in upskilling our scientific workforce. And I'm leading that effort. This is very involved with OpenScapes. I keep looking over here because Julie from OpenScapes is there. So a lot of the things I'm going to be talking about, I have developed in conjunction with Julie. I also showed their hack weeks. A lot of my thinking about how to do training, how to help people learn new tools has been developed by watching people during hack weeks. I observe how they learn. I see what's hard for them and then try new ideas. Okay. So as I said, NOAA Fisheries is embarked on this big effort at workforce upskilling. And this is a little cartoon that we show to kind of like graphically show this of like, so, I don't know, can you guys see this? I don't know, there we are. So we've been working for many years, working in our early adopter group, the group of people who are excited about these new tools, all these things you've been learning about, plus many others. A lot of like changing their workflows, and they're really excited about that. So we've been working with them, developing them. And then now, as I said, we're in this just finished year 1 of this 3-year period. It's focused on crossing what feels like a big chasm from the people who are not just willing, but eager. So going from the eager early adopters, and we're moving into our target population who maybe or might be willing, but maybe not quite so eager. Okay. Hey, come on. There we go. All right. So we've been hearing about like tools and infrastructure, and you need that, obviously. That's really important. But when we're thinking about, okay, how do we get our community to use these tools and this new infrastructure and really do things a different way? we have to think about the people and the teams in the community. How do we help these teams do things differently? How do we help individuals do things differently and learn new things? And we're doing this within in this case, a federal agency. Well, it's within a line office. So it's different. It's not like an academic institution. It's not just like people, just out there who are, joining. It's within an organization. So as we have been working on this and thinking about how we implement this, we, throughout the process, have been really influenced by the ideas around diffusion of innovation. And a core idea with that is when you are trying to spread new ideas, new ways of doing things within a community, within a population, your early adopter group is really, really important. Now, your early adopter groups are not necessarily the ones who innovated. They came up with the new ideas. But they're the ones, they see that new idea and they're like, ooh, wow, that's a good idea. I want to learn that. And I want to not just use it, but I am driven to create things for other people. These early adopters, that drive to create things for others. These are the people who they learn things and then they want to make a tutorial to teach other people to do it. Or they take that idea and they're like, oh, wow, if I can make a package and then people install it, they could do it faster. They're just kind of driven for that behavior. They can be fairly obsessive about it. And it's really important when you are trying to spread ideas throughout an organization that you identify those people. Because you're not going to do it alone. It's not going to be two people who can do it. You need those people who get excited about your idea. So a lot of our work has focused on me trying to figure out how to move the slides forward. There we go. Okay. Oop. Hey, there we go. Great. Okay, so how do we reach these people? What does that look like for us? So I'm going to show you a few different ways that have been really important. I'm going to start with what I would say is the most important one. And that is what are called OpenScapes Champions Cohorts. These are 10 weeks where 40 people come together as a cohort and they opt in. We say, hey, you can sign up. There's no cost or anything, but it's all within our organization. They come and for 10 weeks, they're going to work on changing some aspect of their workflow. Now, it's really important. They come with what they want to work on. It's not that we say, hey, we're going to teach you how to do these things. You're going to just sit in class. They do have some lectures. Of course, they need to learn new things. But the key thing is they're bringing in the thing they want to work on, and they work on that with the peers. They bounce ideas off, and they kind of dedicate these 10 weeks to trying to improve the way they're doing things. So it's a very intentional period of reflection, and it's about workflow. How do they do things? And whenever we describe this, people are like, I have no idea what you're talking about. What on earth are they doing? They're just sitting around, talking. And it's like, no, yes, they do talk. But it looks like this. These are the kinds of exercises. This is a particularly nice graphic one. So first off, we need to get them to talk about what is their workflow. And that is actually a difficult conversation for people because you're in a team, that's a pretty scary conversation because everybody's or most people's workflows are pretty messed up in various ways. And being able to honestly say, hey, yeah, this one's messed up. This is where a lot of errors come in, or a lot of inefficiency. That's a really hard conversation. So we spend like 3 weeks just getting them to feel comfortable enough to talk about hard things. The other thing that comes up is they are scared to say that they do not know what the workflow is. Team unawareness is extremely common, like ubiquitous. So that's the thing. And then we get them, and then they get really depressed because they see how awful things are. And then we need to get them out of that depression and start to see where they want to go and how they can start making steps and moving that. And at that point, that's when we start using these tools. Hey, you can use this. So when I say tools, think about the kinds of things we're learning and other tools. Okay. I'm going to go more quickly through some of the other things that are really important. Second, another thing is our mentors group. These are like our local leaders. These are people who want to take a leadership role locally. They'll organize things. They'll give us feedback about what's important. They'll help co-lead these cohorts. These people tend to come through the champions cohort and they'll self-identify. These people are pretty rare, but they just have a passion for this stuff. Another key part is aligning with allied and adjacent user groups, identifying where the types of people who would want to learn these new tools, where would they exist? So we're teaching a lot of Python tools, and I'm showing here an R user. And so you think, well, wait, wouldn't you do that with the Python group? Well, these are people who program. They like to program, and really there's no particular reason they have to be programming in R. They also, once they learn Python, they'd like that too. We're actually trying to get them to be bilingual, and I'm going to get to that in a moment. All right, and then the last thing I want to talk about is the importance of like communicating and amplifying. We do this so much. We give so many, giving 10 times more talks than you would ever think of. And we're doing this throughout the agency. And this part is really it's really important. And so I think a lot of times you don't think about that, like just talking about things, how important that is. All right. And so what it kind of looks like today is our workforce development. It looks like we have 2 full-time staff. I'm one of them. I've talked about a lot of community building. We have lots of infrastructure work that we've invested in. We have a training Jupyter Hub. You know all about Jupyter Hubs now from Tasha's great talk. And then we have lots of training events weekly, 2 times a week, lots of different things. And then we also have one-on-one support. Okay, how am I doing for time? Okay, I'll go fast on the last part then. Okay, so I told you we have a Jupyter Hub, and you've learned about those from Tasha. So one thing that's hard for us, so here's our Jupyter Hub there, and then you can like here you can just select images. We have lots of different images they can select. This is the main one we use, and you can see it says PyR. It's a Python R image. And so I told you that I've been involved in a lot of hack weeks. I also run a weekly hack hour. And during these times, I'm observing how people, how our R users are interacting with our Python content, especially during hack weeks. I'm kind of watching how they interact. And oh, I guess I should give you a little background before I jump right into the image. Why is this important for NOAA Fisheries? Because our scientific staff is overwhelmingly R programmers. They program a lot, but there are. We need to get more ocean climate data into our models. That means they need to work with the physical and biological oceanographers. They are primarily Python users. All that things you've been watching about like accessing big Earth data and doing things really fast, they were doing that in Python. Yeah, Rust might have been under the hood, but the user interface was Python. So we really need to get our users more comfortable with Python. It doesn't make sense for them to read code how to do this in R. That's not a good use of their time. It's far better for them to learn Python. So, but one of the problems is with the way Jupyter Hubs are often designed is that they're siloed. So they're great. They are incredibly great. But if you look at them, this is a really common way they set it up. So your Python users are going to go in a Python environment. Your R users are going to go in an R environment. And you might think that doesn't matter. It absolutely matters. If you watch in a hack week, all the R users will be on one table. All the Python users over here, they might be in different rooms. The people who develop these images, they're different because you had to have your R people developing the R one. And they are different in all these little ways that just create lots of friction. So when your R users need to run something in Python, they got to start off the Python image, and then it's slightly different in, oh yeah, it's just like if Okay, I'll show you an example. Like, in the R image, the username is our studio, and in the Python one, it's Jovian. You would think, hey, Eli, that doesn't matter. As an instructor, I've spent so many hours just trying to explain, no, it doesn't matter. Look, just change the username, blah, blah, blah. Yeah. So those little things make a big difference. So a big thing that we worked on is creating an image where we merge that Python and R. And so everyone's using the same image. And the key thing that was really, really hard, we spent like 3 years. So we're on version 3. Version 1 and 2, we tried to, under the hood, tried to kind of merge them. And I was working with Carl Bettiger and Luis Lopez. They're, very good. And we just had endless weird bugs because all this underlying things, Proj, GDAL, it was endless complex. And also we got into maintainer nightmare, where we were spending too much time maintaining the Docker image. So what we did is a new strategy, and this has been working great. It's now been a year heavily using it. And we do it this way. In the image, it's one Docker image if you use it, but actually under the hood, all the Docker code that creates the image on the Python side is from the Pangeo notebook. So we let that community figure out how to create a really good Docker file. For the R geospatial, we let the R community figure out how to make a really good Docker file for their community. What we figured out is how to have them both in one image and not interact with each other. From the user perspective, though, they see this. So they can decide however they want to interact with the environment, with the code. So I can click on that Python 3. It actually should say Jupyter Lab because they can run R in any of these. So they can decide they want to run R in Jupyter Lab. That's fine. That's just the IDE. If they get the Python kernel, it's that Pangeo Python kernel. It works beautifully. If they say, I want to use the R kernel, they work in the Rocker environment and it works beautifully. There are no hiccups, and we don't have to worry about maintenance because it's this other community that is maintaining those Docker file instructions. All right, I'm going to stop there and encourage you, if you want to play with this. If you're at NOAA, you can actually jump on a Jupyter Hub. But if you want to learn about PyRocket Base and our design, we have a nice documentation there. All right.
Thank you so much, Eli. And thanks everyone for attending. Thank you again to all of our speakers. I'm going to ask if people want to ask Eli questions to, touch base in the hallway. I think people are already enjoying some coffee and you might enjoy that too. So thank you, everyone. We'll be in here at 4 if you want to join us for a working session.